Hello, dear students. Welcome to the second lecture on heat exchanges. In the last class, we had seen the classifications of heat exchanger, overall heat transfer coefficient, and the fouling of heat exchanger. In this lecture, we will see the derivation of log mean temperature difference. Before going to the derivation of log mean temperature difference, let's see the heat transfer in a heat exchanger. We know that in a heat exchanger there are two fluids flowing, irrespective of whether it's a parallel flow, counter flow, or any other type of a heat exchanger. So one is a hot fluid and another is a cold fluid. So before actually starting the derivation and other calculations in a heat exchanger, let's first be familiarized with the different terms to be used in a heat exchanger. Here in this slide you can see Q stands for heat transfer or heat exchanged in a heat exchanger, which will have a unit of watts. As you know, in all our calculations in heat transfer, Q stands for the rate of heat transfer in watts. Then here m dot stands for the mass flow rate. M dot with a suffix m dot h stands for the mass flow rate of the hot fluid, whereas m dot suffix c stands for the mass flow rate of the cold fluid. Similarly, c, this is small c, so small c with a suffix h stands for the specific heat of the hot fluid, and c suffix c, small c suffix c is the specific heat of the cold fluid. And the notations for temperature also, capital T stands for the temperature. Basically we have temperature of the fluids. So T suffix HI, THI means the temperature of hot fluid at the inlet, and THO is the temperature of the hot fluid at the outlet. Similarly, TCI stands for the temperature of cold fluid at the inlet, and TCO temperature of the cold fluid at the outlet. Now we can have the calculation. Q is equal to m dot h ch into thi minus tho. Thi minus tho is a drop of the temperature of hot fluid temperature difference. So hot fluid enters at a higher temperature Thi and leaves at a lower temperature Tho. So the heat lost by the hot fluid is m dot h ch Thi minus Tho, which can be written as, so we take the product of m dot h into ch, mass into specific heat. Mass into specific heat is nothing but heat capacity. So mass flow rate into specific heat will give the heat capacity rate of the hot fluid. So here we use capital C. So capital C suffix H is the heat capacity rate of the hot fluid, which has a unit of watt per Kelvin into Thi minus Tho. Similarly, heat transfer can also be written as the heat gained by the cold fluid. So m dot c cc into tco minus tci, whereas tco minus tci is the increase in temperature of the cold fluid as it receives energy. So m dot c cc, we will write capital C suffix c. This is the heat capacity rate of the cold fluid, heat capacity rate of the cold fluid into TCO minus TCI. So heat transfer can also be written as CC into TCO minus TCI. Now, in the case of a heat exchanger, the heat exchanged can be written as a product of overall heat transfer coefficient into the area multiplied by T hot minus T cold. Temperature difference between hot water and cold. I mean hot fluid and cold fluid. And suffix mean is used here. I have used this mean intentionally because some of us know that the temperature difference of hot and cold fluids will be changing from point to point. So we need to have a an average or a mean of temperature difference over the entire area. So we need to find out an equation for this step, some sort of a mean of the temperature difference between hot and cold. This is the aim of this. So this can be found out by suitably using the energy balance and convection equation. This is our aim. Our aim is actually to find an expression for T hot minus T cold mean. Let's see how we can derive this. So now we'll go to derivation of the mean of temperature difference between hot and cold for a parallel flow heat exchanger. So we know that for a parallel flow heat exchanger, hot and cold fluids flow in the same direction. So here we can see that hot fluid enters at a higher temperature THI and leaves at a lower temperature THO. So whereas cold fluid enters at the same end at a temperature TCI, and as it flows in the along the heat exchanger tubes or passages, its temperature increases to TC out. Let's now choose select a small area of the heat exchanger. Okay, what happens to the temperature of hot and cold fluids as it flows over a small area or a small distance in the tubes? Here, as it flows over a small area dA, this figure is taken from one textbook where they have slight difference in the notations. They are using suffix s for the surface area, but in my presentation I am not using this suffix s for the surface area. Similarly, for out conditions I am using O only, whereas in this picture they are using out. So please pardon me for this difference in the notations, a small difference in the notations between the figure and the equations. So I believe that there is not much of confusion caused due to this difference in the notations. So let's see, as the hot fluid flows over a small area, its temperature difference, a small difference in the temperature occurs. Let it be dTH, and there is a small difference in the temperature for the cold fluid, and let it be dTc. And let's also assume that the temperature difference between the hot and the cold fluids is delta T. So this is delta T. Delta T is equal to T hot minus T cold, TH minus TC. Here we can see that this TH varies from THI to THO for the hot fluid, and this TC which varies from TCI to TCR, which is for the cold fluid. These are the temperature differences. So in that regard, here we can see that at the inlet, that is inlet end, this end we can call end 1, and the other end we can call end 2 of the heat exchanger. So at the end 1, at end 1 of the heat exchanger, temperature difference between hot and cold fluids is delta T1, whereas at the end 2 of the heat exchanger, the delta T2. T hot minus T cold at the end 2 is delta T2. Now, this is actually an elemental area. So, let's see the heat exchange or heat transfer in the elemental area. Small heat transfer in the small area or elemental area. So, we can write the small heat exchange over the elemental area delta Q is equal to negative m dot h ch into dth. M dot h ch into dth with a negative sign, that's equal to minus capital CH dth, or which will give us dth can be written as delta Q divided by CH with a negative sign. So dth is equal to minus of delta Q divided by CH. Why we have a negative sign here? Because dth decreases in the positive direction. The flow direction of the hot fluid is considered as a positive direction in all the cases. So from left to right, the temperature of hot fluid decreases. So in order to make this term positive, we introduce a negative sign. So dth is equal to minus delta Q divided by CH. Or in other way, it is lost by the hot fluid. So the sign convention for heat will be with a negative sign. So dth is equal to minus dq by ch. Similarly, for the cold fluid, in terms of cold fluid, the same delta Q is received by the cold fluid whose temperature increases. So whose energy difference can be represented in terms of mass flow rate into specific heat into delta Tc, that is equal to Cc into dTc, not delta T etc, which will give us dTc can be written as delta Q divided by Cc, the same delta Q divided by Cc. Here we did not use a negative sign because here dTc is increment, temperature increases, and also, or in other ways, we can see that with regard to the cold fluid, delta Q is positive because it receives heat. As per the sign convention in thermodynamics, this is positive. So anyhow, we will write dTh is equal to minus delta Q by CH and dTc is equal to delta Q by Cc. We can write them as two equations, equation 1 and equation 2. So equation 1 minus equation 2, we can write dTh minus dTc, which can be written as derivative of Th minus Tc. Derivative of Th minus Tc is equal to minus delta Q by Ch minus delta Q by Cc. So minus delta Q taken outside into 1 by Ch plus 1 by Cc, whereas Ch is the heat capacity rate in watt per Kelvin and Cc is the heat capacity rate of the cold fluid, again in watt per Kelvin. Let's call this equation 3. Now we can write delta Q can also be written as overall heat transfer coefficient into area into change in temperature. So for the small area dA, we can write delta Q is also equal to U into small area dA into temperature difference between the hot and cold fluids, the Th minus Tc, which is equation 4. So now we can represent the same thing in using two equations, comparing equation 3 and 4. Now we have a delta Q appearing in equation 3. This delta Q is written as U into dA Th minus Tc. So we substitute for dq from equation 4 into equation 3. We can write d of Th minus Tc. Th minus Tc is equal to minus of Now dq is written as u dA th minus tc, u dA th minus tc into 1 by ch plus 1 by cc. It is clear. There is no scope of any doubt. Now rearranging this, we'll take this th minus tc to the left side, d of th minus tc divided by th minus tc. D of th minus tc by th minus tc is equal to minus u into th minus, sorry, this is taken to the left side, 1 by ch plus 1 by cc into dA. So this is just this th minus tc is taken to the left side. Now this is t of something divided by that something is equal to minus u into 1 by ch plus 1 by cc into dA. Now we have a differential form. Now integrate over the entire area from end 2 to end end 1 to end 2. So integrating this, we will get what is the integral of this. This is equal to logarithm of th minus tc, integrating over the entire area from end 1 to end 2, which will be equal to minus u into 1 by ch plus 1 by cc into integral of dA. Integral of dA will be the area, total area of the heat exchanger. So now remember that th and tc varies from inlet end to the outlet end, whereas u, ch, cc, etc. are constants. So now integrating over the entire area of the heat exchanger surface, we will get log the log tho minus tco. This is a second end. Final minus initial. Log tho minus tco minus log thi minus tci, which is written in a single step as logarithm of tho minus tco divided by thi minus tci, which is equal to minus u into 1 by ch plus 1 by cc into integral of dA will be a. So this is a integrated form and applying the limits. This is simple mathematics, just integration and applying the limits. We will get this in terms of the inlet and outlet temperatures of hot and cold fluids. Now one thing, let's go back to a previous slide here. Okay, Q is equal to CH into THI minus THO. So 1 by CH is equal to, or CH is equal to Q divided by THI minus THO, or 1 by CH is equal to, this is taken to the other side, 1 by CH is equal to THI minus THO divided by Q. Similarly, 1 by CC is equal to TCO minus TCI by Q. Whether it's a parallel flow or counter flow, this equation will be the same. So 1 by CH is equal to THI minus THO by Q, whereas 1 by CC equal to TCO minus TCI by Q. Now let's use this relation. 1 by CH equal to THI minus THO by Q, and 1 by CC is equal to TCO minus TCI divided by Q. So substituting this, we will get log THO minus TCO divided by THI minus TCI is equal to minus U into area into THI minus TCO divided by Q minus TCO minus TCI divided by Q. So Q is taken as a common dividend. Okay. Sorry, common quotient. I think it's quotient. Which is equal to this negative sign is taken inside to the numerator. We have UA minus TCO will become plus TCO. So TCO minus minus THO will become plus THO. So THO minus Sorry, there is a mistake. This is to be positive. So I'll correct the mistake now itself. Uh, this should be positive. So now after taking negative also along with this, uh, minus THO will become plus THO, and minus THO plus THO, and plus TCO will become minus TCO. So THO minus TCO, and minus THI minus TCI, minus THI minus TCI. So all of you, I advise all of you to write this derivation in a paper and make sure that you are getting all these terms. There is no um, confusion here. UA into negative is already taken inside this THO minus TCO minus THI minus TCA divided by Q. Now we can see THO minus TCO is the temperature difference between hot and cold at the outlet end, and THI minus TCI is the temperature difference between hot and cold at the inlet end. So now this is a left side and this is a right side. We have a Q also here. Now we will write this in terms of Q is equal to. So we take this, yeah, we take this Q to the left side. So Q is equal to UA is retained in the right side into THO minus TCO minus THI minus TCI divided by log of THO minus TCO by THI minus TCI. So temperature difference minus temperature difference at the second end minus temperature difference at the first end divided by log of temperature difference at the second end by temperature difference at the first end. So UA into something, some term of temperature, combination of temperatures. Now this will be something like, now you compare the convection equation. Q is equal to overall heat transfer coefficient to area into temperature difference. Now that temperature difference, let's write this as UA into mean temperature difference. What type of a mean is that? This is called log mean temperature difference or delta T. So delta T, UA into delta T, log mean of the parallel flow heat exchanger. Log mean parallel flow heat exchanger. So log mean temperature difference. So this is called a log mean temperature difference, or in short we will say LMTD. LMTD of parallel flow heat exchanger is written as THI minus. Now we can uh, write either this as THI minus TCI minus THO minus TCO divided by ln of this. We take the negative of this and negative of this, reciprocal of this. We can write either like this or like this. There's nothing wrong in it. This is called a log mean temperature difference. This is a expression for log mean temperature difference. Okay. Now let's also see the derivation of LMTD for counterflow heat exchanger.